In the early days of the internet, a server with 10,000 concurrent users was considered a massive engineering feat. Today, Discord routinely handles servers with millions of active participants, most notably during events for communities like Midjourney or Genshin Impact, where a single server can peak at over 12 million concurrent users. This isn't just a matter of adding more RAM or faster CPUs. At this scale, traditional architectural patterns break down. When one person sends a message, the system must figure out how to deliver that data to millions of others instantly, without melting the network interface or overwhelming the CPU. To understand how Discord achieves this, we have to look past the interface and into the unique properties of the Erlang virtual machine and a specialized distribution layer they built called Manifold. Discord's backend is primarily written in Elixir, running on the Erlang virtual machine, or Beam. Unlike traditional languages where threads are heavy and expensive, Beam processes are incredibly lightweight. Each process has its own tiny memory heap, starting at just a few kilobytes. This allows Discord to spawn millions of concurrent processes on a single machine, one for every user, every guild, and every internal service. These processes communicate strictly through message passing. There is no shared memory. If process A wants to talk to process B, it sends a copy of the data. This isolation is the secret to Discord's fault tolerance. If one user's process crashes due to a bug, it doesn't take down the entire server or affect any other users. The system simply restarts that specific process and moves on. However, this copy everything model creates a massive problem when you scale to millions of users.
The primary challenge in a large Discord server is the fan-out problem. Imagine a user in a server with 1 million members sends a single message. The system must now deliver that message to 1 million separate processes. In a naive implementation, the process representing the guild would iterate through a list of all million users and send a message to each one. This is an O of N operation. Because these users are spread across hundreds of different physical servers in a cluster, this means the sender node has to serialize that message and send it over the network 1 million times. Even with high-speed 10 gigabit networking, the CPU cycles required to serialize and push those packets create a massive bottleneck. The sender node's network interface becomes a literal scorched earth zone, and message delivery latency spikes from milliseconds to seconds.
To solve this, Discord engineers built a library called Manifold. Manifold changes the communication topology from a flat list to a distributed tree. Instead of the sender node talking to every user individually, it identifies which remote nodes in the cluster host the target users. The sender node then sends exactly one message to each of those remote nodes. When that single packet arrives at the destination server, it is then fanned out locally. Because memory access within a single machine is orders of magnitude faster than network calls, the destination node can efficiently distribute the message to thousands of local user processes simultaneously. This effectively shifts the heavy lifting of message duplication from a single bottlenecked sender to the entire cluster, parallelizing the workload and reducing network traffic by over 90% in large servers. Messages aren't the only traffic. Presence updates, the green dots showing who's online, are constant. In a 12 million user server, if every person's status change was sent to everyone else, the bandwidth would be consumed entirely by user X is now idle notifications. Discord uses a lazy presence system. You only receive updates for the people you can actually see in your current view. If you're looking at a specific channel, the backend only tracks and sends you updates for the members in that channel's list. As you scroll, Discord dynamically subscribes and unsubscribes you to different member chunks. This turns a global O(n) squared problem into a localized O constant problem, ensuring that your client isn't processing thousands of invisible updates every second. Despite the power of Elixir and Manifold, Discord hit a wall with read states, the system that tracks which messages you've read. This service was originally in Elixir, but because it held billions of small objects in memory, the Erlang garbage collector struggled. Every few minutes, the GC would trigger a stop-the-world event to clean up memory, causing massive latency spikes. To fix this, Discord rewrote the read state service in Rust. By moving to a language without a garbage collector and with manual memory management, they eliminated those latency spikes entirely. Rust allowed them to pack data much more tightly in memory and utilize every bit of CPU performance. Today, Discord's architecture is a hybrid. Elixir provides the high-level orchestration and distribution, while Rust handles the performance-critical, memory-heavy data structures. Discord's ability to support 12 million concurrent users isn't the result of a single silver bullet technology. It's a layered defense against complexity. They use Elixir for its massive concurrency and fault tolerance, Manifold to solve the network fan-out problem through hierarchical distribution, and Rust to eliminate garbage collection bottlenecks in data-heavy services. By understanding the physical constraints of networking and memory and choosing the right tool for each specific bottleneck, Discord has built one of the most resilient and scalable real-time communication platforms in existence. Next time you send a message in a massive community, remember the invisible tree of nodes working to deliver it in milliseconds.